At the microscopic level, the physical world is mostly a void. The atoms that form our surroundings are almost entirely empty space. If you expanded a single atom to the size of a classroom, the nucleus would be the size of a pinhead resting in the center. That tiny core accounts for over 99.9% of the atom's entire mass. In the early 20th century, Ernest Rutherford faced the challenge of measuring this core without the help of visible light. The nucleus is far too small to reflect the wavelengths we use to see. To map the unseeable, physicists had to hurl microscopic projectiles at the atom and measure how they bounced back. Rutherford's methodology involved firing positively charged alpha particles, essentially helium nuclei, at a thin sheet of gold foil. Because the gold nucleus is also positively charged, it exerts a massive repulsive force. As an alpha particle rushes in, it slows down, diverted by an invisible electrical shield. By tracking a particle on a direct head-on path, researchers could find the exact point where its kinetic energy is exhausted. It halts and reverses direction at a point called the distance of closest approach. For a 5.5 MeV alpha particle, this distance is exactly 4 × 10 to the negative 14 meters from the center. Because the particle never touches the core, the physical boundary of the nucleus must be smaller than this stopping distance. These experiments proved the nucleus was incredibly small, but they only established a maximum boundary limit, leaving the true surface unmapped. Higher kinetic energy would seem to provide a closer look, pushing the alpha particles deeper through that electrical resistance. However, crossing a certain proximity threshold triggers the short-range strong nuclear force. This force alters the particle's trajectory, invalidating the Coulomb calculations used to determine distance. Alpha particles are too heavy and too charged for precise mapping. Their interaction with the target's internal forces distorts the measurement. To find a more accurate edge, physicists swapped heavy alpha particles for fast-moving electrons. Electrons do not interact with the strong nuclear force. They penetrate deeper, allowing researchers to map the actual physical boundary of the core. By bombarding various elements with these electrons, physicists built a comparative dataset of nuclear sizes. These measurements required a new unit of precision, the femtometer, which is 10 to the negative 15 meters. By using a probe immune to the nuclear force, researchers finally possessed a ruler capable of finding the exact edges of the atom. Electron scattering revealed a uniform mathematical rule governing elements across the periodic table. The radius of any nucleus is defined as a constant, R0, multiplied by the cube root of the mass number, A. That constant is exactly 1.2 femtometers. Therefore, a nucleus's total volume scales in direct proportion to its protons and neutrons. Adding particles to a nucleus does not increase internal crowding or compression. The outer boundary simply expands to accommodate them. This is often called the liquid drop model. In this model, the nuclei of carbon, iron, and gold are different sized drops of the same fluid-like substance. Since volume and mass scale together, nuclear density is a universal constant for every element. This density measures approximately 2.3 × 10 to the 17th kilograms per cubic meter. Ordinary water has a density of 1,000 kilograms per cubic meter. By contrast, a single cubic centimeter of nuclear matter would weigh over 200 million tons. Neutron stars share this exact structural packing. The most extreme objects in the cosmos are built from the same dense matter found in our bodies.